we're jumping straight into 3 foundational statistical tests that every researcher absolutely needs to know: reliability, t-tests, and ANOVA. Let's get right to it.
So here's how we're going to tackle this. First, we'll check if our survey is even worth using. Then, we'll get into comparing 2 groups. And finally, we'll scale up to comparing 3 or more. It's the logical flow of a real research project. All right, first things first. Before you can even think about analyzing your results, you have to prove that your measurement tool, your survey, your test, whatever it is actually consistent and trustworthy. This is the foundation everything else is built on.
I mean, really, this is the first question you've got to ask yourself. If your data isn't reliable, then honestly, none of your conclusions will be either. So how do we actually check for that?
It all comes down to this one simple word: consistency. The weighing scale example is perfect. It's the same idea with a survey. If you're measuring something like motivation, a truly motivated person should answer all the motivation-related questions in a consistently positive way. If they don't, something's wrong with the questions, not the person. So we measure this consistency with a score called Cronbach's alpha. And this table is your cheat sheet. For most scientific research, you're really aiming for that good zone, somewhere between 0.8 and 0.9. 0.7 is, well, it's acceptable for maybe a quick classroom poll. But anything below 0.6, that's a huge red flag. Your survey has serious problems. But here's something a lot of people miss. Just because you get a good overall score, say a 0.85, doesn't mean you can just pack up and go home. You could have a bad question hiding in there, quietly dragging your whole score down.
So you have to become a bit of a detective. You need to hunt for those bad apples, those questions that are just off. Maybe they're worded weirdly, or they're measuring something totally different from the rest. How do you find them?
You've got 2 main tools in your kit. The first is corrected item total correlation. Think of it as checking if a question is singing in tune with the rest of the choir. If that score is below 0.3, it's out of key. The second tool, alpha if item deleted, is even more direct. It literally tells you, hey, if you get rid of this one question, your overall score would jump up. That's a pretty clear signal to cut it.
And the best part is, actually running this in a program like SPSS is super easy. It's just 3 steps. You prep your data, you click a few buttons to run the analysis, and then you look at those key numbers we just talked about. Simple as that.
Okay, so we've confirmed our survey is solid. Now we can actually use it to do something interesting. This is where we start answering our real research questions by comparing different groups.
Let's take a classic modern-day question. You've got 2 groups of students. One gets their writing feedback from an AI, and the other gets it from a human teacher. At the end of the term, who has the better writing scores? How can you tell if there's a real difference?
Well, for this job, you need a t-test. But you have to pick the right one. It's simple, really. Are you comparing 2 completely separate groups, like our AI versus teacher example? Then you need an independent samples t-test. Or are you comparing the same group of people at 2 different times, like their scores before and after a training program? That calls for a paired samples t-test. Now, the t-test spits out a really important number called the p-value, and the magic number you're looking for is 0.05. If your p-value is less than 0.05, it means the difference you're seeing between your groups is almost certainly real and not just some random chance. We call that statistically significant.
But hang on a second. Getting a significant result is exciting, but it doesn't tell you the whole story. Significant just means a difference exists. It doesn't tell you if that difference is tiny or massive, trivial, or game-changing.
For that, you need to look at something called effect size. This tells you the magnitude of the difference. Is it a small effect, a medium one, or a large one? This is what tells you the practical importance of your findings. A tiny effect might be statistically significant, but who cares? A large effect, though? Now that's something that could actually change how we do things in the real world.
So t-tests are great when you have 2 groups. But let's be honest, the real world is often a lot messier. What do you do when your research question involves more than just a simple A versus B?
Exactly. What if you're not just comparing 2 methods, but 3 or 4? You can't just run a bunch of separate t-tests. That's a statistical no-no, and it actually increases your chances of being wrong. For this, you need a more powerful tool.
And that tool is called ANOVA. It's specifically designed to compare the averages of 3 or more groups all at once in a single test. Basically, it's a super efficient way to see if there's a meaningful difference somewhere among all your groups.
The best way to think about the main ANOVA test is like a smoke detector. It goes off beeping loudly to tell you, hey, there's a fire. There's a significant difference somewhere in your data. But, and this is a huge but, the smoke detector doesn't tell you
which room the fire is in. It doesn't tell you if Group A is different from Group B or if Group C is different from both of them. It just screams, there's a problem somewhere.
To actually pinpoint where the differences are, you need to run a follow-up test. These are called post hoc tests. It's a fancy name that just means after the fact. These are the tests that go in and check every possible pair of groups to find out exactly who is different from whom.
So, which post hoc test do you use? Well, you first have to check if your groups have a similar spread of scores. If the spread or variance is about the same for all groups, you use a test like Tukey's. But if one group's scores are all bunched up and another's are all spread out, you need a different test, like Game's Howl. Getting this right is crucial for getting an accurate answer.
And this brings us right back to the most important question of all. Just because you find a statistically significant result, does it automatically mean it's important in the real world? No. The statistics give you a clue, but it's up to you, the researcher, to look at the effect size and the context to decide if it truly matters. And that's the real heart of doing good research.